Okay, hello everyone. So right now I'm in a 7 week sprint of multivariable calculus, and although I know I'm beginning to start digging more into machine learning and deep learning specifically for the next thing I want to target, which is the edtech, because one thing that kind of stuck with me is whatever advantages you have, use them and exploit them. And I think that I don't know, so success does come when you lean into your unfair advantages. I know one of them is with education, mostly because I have a lot of people who, like, my father was a teacher. I got a couple aunts that are teachers. There was basically a lot of the circle was a lot of teachers, so I kind of got to see a little bit of inside scope. I also like teaching concepts to one another. I mean, this is what I'm doing, and I guess the intentions of these semis is to really move ahead with the math, because I do know the higher level math definitely is going to be useful for this, and then on my own take to do the computations and whatnot. And I'm currently building that project that I think that I would like to take it as far as to see, who knows, see if it gets funding or whatnot. But right now is to build the MVP. I'll get the feedback and reiterate as I can, because I know the feedback will definitely be useful. However, for Calc 3, or multivariable calculus, whatever you call it, right now I'm going to give you the first 3 lessons that I have in distilled notes, some examples as well. And my bad if the screen is a little bit dark, blurry, but right now I'm trying to do this the best I can. Right now, I just want to distill the ideas, pretend as if I was speaking to someone on the other side of the screen, and explain it to them. Because if I can't explain it well enough, that means you don't understand it, and which means I got to go back to the drawing board or learning board and reconsider, so that I know that when it's time to start building things that are definitely math heavy dense, I'm good to go and I can deliver for not just myself but for the rest. So, chapter 11.1, vectors. So I already mentioned in the Medium article that I will upload this video is vectors. Vectors are this line in space, and just like how in regular lines in, let's say, algebra, pre-calc, calculus, it's just that it's a line. Except the difference is, in regular lines have direction, but now with vectors you add a second component, which is speed. For speed, you could call it magnitude. The technical word is called magnitude, but for those who don't know what that is, you could also say that magnitude is the same as length. So a length and a direction. So the analogy that I would use is like a car, where, cool, you could say you went 60 miles. That's your direction. Or, yes, that's your direction. Or length, I would say 60 miles. My bad. You say it's a magnitude or length. But where? North, south, east, west, where? Northeast, northwest. And that's where the direction comes in. So that's what the vectors would describe in some sense. It's in 3D space. You have to consider, okay, you have because anything that's in 3 dimensional space, you have these areas where you may start at one place, but now you can move in whatever direction you want. And it's almost as if when you're graphing 3D space, it's similar to a compass, where you have north, northwest, west, southwest, south, southeast, then east, and then northeast, and you're back to north. Sometimes when you're driving with the car, that's how the 3D spaces are thought of, and vectors do well at that, because sometimes you can change direction, or sometimes you can change the length or speed, magnitude of wherever you're trying to go. And at least in the mathematical concept, the vector, that can also switch. And I'm not going to go too deep into the what vectors can do, like multiplied by constants and whatnot, because that's on the article. Right now, this is more of the formulas and the theorems that come with it. That's what this video is going to be about. Okay, is the for the first 3 lessons, what are the theorems? How would I explain to you without using any graphs, without anything at all? Because there's plenty of resources out on the internet to figure that one out. But I'm going to try and explain the theorem as if I don't know, you're 5. All right. So here we go. All right. So adding and subtracting vectors. So let's say these two are vectors, right? I mean, one of these pencils are smaller than the other, but whatever. So let's say each pencil was a vector, or a vector that had both direction. So let's say this vector goes, or this pencil goes up straight, and then this vector, let's say, goes to the right. Both have a direction and speed or length. So one is smaller than the other, for the pencil, by the way. If you want to add a vector, if you want to add two vectors like this, let's say the vectors are going like that. What you do is, let's say this was vector A and vector B. Depending on the letter, but the one that's the letter that comes first in the alphabet of whatever, that one you would typically want to add first. So let's say if it was vector A plus B, then you would go like this. And by the way, it actually doesn't really matter how you add the vectors in a sense, because a vector A plus B is the same as B plus A. Nothing really changed. It's just different ways of orienting. It's commutative. I'm pretty sure that's the word. And so what you do is you just pretend as if you were attaching them in a sense. And when you attach them, the vector that connects here to here is vector V plus W, or A plus B, my bad. And that's what happens if you were to add these two together. So in a sense, when you're adding vectors, it's like saying, let's make a triangle with these vectors. So you have to attach to try and make that vector. But let's say you were subtracting vectors, where let's say you were subtracting vector A minus vector B. When you're doing vectors and they're negative, all that you're doing is you're changing the direction of where the vector is pointing. So if this is negative, or vector A minus vector B, instead of going this way, it's going that way. That's all the vector is. So for example, it's like with north and south, for example. If you all of a sudden you went 10 miles north and then 20 miles south, you're going to the right 10 and then back down. Or I guess north and south. You're going up 10 and okay, now you're going back down 10. So that's kind of what vectors do in a sense. Is if a vector is negative, all you do is change the direction of whatever it was pointing. So it was pointing this way, it was pointing that way, just go that way. And then there, whatever is from here, whatever's from here to here, that's also specifically the new vector. But it all really comes down to the arrangement of these vectors, because this gives you perfectly. But let's say if it was this, then that may look a bit different. Because then vector A minus vector B would be from this point to that point. You're subtracting two different lengths of lines, but then the direction as well. But typically it's just length that you're trying to find out in a sense. So that's adding, subtracting vectors in basic sense. The notations, I'm not really going to go over that one. That I think I already put that there, but let's see. Position vectors, those are just like any regular type of vectors where it's just a line pointed in a specific direction that has a certain amount of length. The special thing about a position vector is it starts at the origin 0, 0, 0. Why 3 zeros? Because we're now talking in three dimensions. You have to consider an x, the x-axis, the y-axis, and the z-axis. But that's really the only difference. It's like any other line that in regular 2D that starts with the origin. That's all a position vector is you don't really consider when you're doing vector analysis or like vector math in a sense. The reason why everyone likes position vectors is, let's say you have to multiply or subtract or add. It's just by, let's say if it was the vector was 1, 2, 3 at the end point, but the origin was at 0, 0, 0. I mean, what's subtracting? If you wanted to find the length of the vector, then you could just do 1 minus 0, 2 minus 0, 3 minus 0. It's nothing, or 3 plus 0 if you wanted. So that's the beauty of vectors, of a position vectors. It's at the origin, easy math in a sense. And it only starts at the origin, correct? I mean, to find the slope in a sense of a vector, let's say if it was, let's go back to 2D. And this for vectors, this thing only works for vectors in 2D, because then when we go in 3D, we kind of lose the sense of a slope. But if we had a vector in 2D, in 2 dimensions, to find the slope, it's basically like any other thing, y2 minus y1 divided by x2 minus x1. So nothing new there. But we're going to find out about something that's known as the length of a vector. There's this funky notation. It may look like an absolute value, but from the person I've been learning online for these 2 weeks prior to the actual class, because technically it's a 5-week class, but I'm not going to wait for the teacher to hit me with his material. I'm going to take this first step. So from Professor Leonard's, obviously, he puts two absolute brackets looking like, because some people think, oh, it's an absolute value, and it's really not. It's just, I don't know, mathematicians. And to find the length of the specific vector, what you would do is get whatever the current the two values, I guess, in a sense, which is where does one vector, where does the m, no, not the endpoints, but I guess the way I would say is, where does it start, where does it end? Subtract those values, and that's what you get in a sense of, okay, this is the total sum of my x length, and this is the total sum of my y length. So you could say, and that would be your v1 or v2, your vector, and your vector values for x and your vector values for the y, which are denoted as v1 and v2. Square them, and then the square root, that would find you the lengths. I know that one isn't as well said. I would need to show the board for that, but yeah, I would definitely need to show you guys an example for that one. So, and actually I got one. So, and that thing that we describe as, in terms of what is that length of the vector, as I mentioned in the beginning, that's the magnitude. The magnitude is just, all right, how long is this vector, this line? So, damn, I really hope that the computer. Oh, okay, good. So here's the example that I made, which is find the slope and the magnitude of the vectors. And I have the vectors here. Vector v starts at the origin, so 0, 0. These are this isn't 2D, by the way, so not 3D. And starts at 0, 0, vector v, and it ends at 5, 2. Vector w starts at 1, 2, and then it ends at 6, 4. To find the slope of something of 2D, you just do the y values of the vector, so y2 minus y1, and then the x values of the vector. So for vector v, x1, y1 is 0, 0. That's the origin. And then x2, y2 is 5 and 2. So for y2 minus y1, 2 minus 0 is 2, 5 minus 0 is 5. Easy. And then for the slope of w, it's we start at 1, 2 for x1, y1, and then for at the end point, it's 6, 4, so x2, y2. 4 minus 2 on the numerator for the y values is 2, and the next value 6 minus 1 is 5. So the slopes are the same. Yes, there's a concept that we'll describe about that. But for the magnitude, or if you want to find the length of something, what we in a sense just did with to find the length of those vectors, what you do is whatever values you got for the x value and the y value. So for, let's say, the vector v, because that's position vector, let's just make it easy on ourselves. It's v1 plus v2, and then you square that value and then square root it. V1 is what happens when you subtract the x2 minus x1 of that vector, and then v2 is what happens if you subtract y2 minus y1. So hopefully I'll explain it too. So that's magnitude, that's how we or length, that's how we describe it. And then this was what happened when we subtracted, right 2 minus 0. So that was our x values, so 2 minus 0. And then this is 5. Hopefully my 5s look well. And 5s, which was, where did it go? Oh yeah, right here. So 5, 0. And does it matter which order? It really doesn't. You're getting the same answer. That'd be square root of 29. So that's how you would find the length of a vector is subtract the x values from the start to the end of the vector, and then you add the y values, or not the y values, but you subtract the y values and then add it into v2. Then you square both of them, and then take it over the square root. For those who are wondering specifically, okay, but how come, like, why the squaring, why the square root? In, I guess the way that I would describe this for the ones looking over here is you're going from the origin all the way to the endpoint, right? I guess you could say where the end of the vertex is. So in a sense, there you have already found its entirety of its length, but in a sense we have already doubled it. But if we were to, let's say, just not square it at all, like what's the point if we're gonna square it again and then having to square root it? Well, sure, fine, we could do that. However, we're gonna end with just half what we had. So we must square and then we must square root. So it would only give us essentially half the image. And I mean, these are just shortcuts, but this doesn't really help us in anything. Yeah, I did describe the unit vector in here in the article. Standard basis vectors. Theorem extra notes. Standard basis. Oh, okay, so there's these funky letters that are gonna look. They're most likely they're gonna be I and J, and they look like they have a little hill on top of the letter. What that really is, it's an abbreviation, or you're simplifying for describing where a vector starts and a vector ends. If you were to start at the x at the origin, then going one value to the left and to the right, it's kind of like it's for specific units, or what is the most basic vector that one can have. In a sense, it's like the standard units, but for vectors, in a sense. So, and for the x value, you would give it the letter I with that weird hat, and then with these brackets 1, 0, hopefully. Right here. That's for the x. The standard for what's the how we can use it when we're trying to go for a very long vector. How can we just simplify it for every step we take? And that's for j. That's for y values. And we would go one step to the right for x, but we're not moving anywhere up or down the y-axis. That's what stays at 0. I mean, the rest is just like a mini proof and examples, but that's pretty much the basis of all of it. Is we, in an attempt to simplify and as much as we can once we're moving up very large vectors, and sometimes even with fractions in there, we don't want to really write all that out. So we kind of said, all right, what's the base? What's something bit standard that everyone can agree on in a sense, and say, all right, if we move up x steps or n steps, then how can we denote that? Well, if we move up, let's say, what, 5 steps to the right, or 5 steps right of x, and then 2 steps down from y, how can we denote that? Well, we can say that that for every 1 step right and left of x, we can denote that with that abbreviation I. And then all we do is, all right, how many steps to the right or to the left we took? If we went to the right, it's a positive x, so we would put the constant value to the left of the I. So I guess, for example, here, this is the 3, and then that positive I, but that positive I was right here. That's that notation, because the real answer we have would be right here, 3 comma -2. But sometimes we need to say, cool, but when we eventually go to 2 or 3, it's like, okay, but is that our x, that our y, is that our z? That helps us notate that, oh, okay, that at this point we're gonna move 3 to the right, then we're gonna go 2 down. So that's essentially what this vector means. And also because this means a position vector, which means we start at the origin. So that means we start at the origin somewhere. We're gonna start at the origin, but then we're eventually gonna end at these numbers. Position vectors have those weird triangles. Not triangles, but it's like those code brackets in a sense. That's specifically just for position vectors that have the origin at 0, 0. If you ever write something in parentheses in in vectors, you're describing a point on a vector. You're not describing the actual vector itself or that length in that direction. You're just describing, oh, at some point in the graph, there's in some points on the vector, there's this thing that exists. That's the difference. So anytime you see those weird brackets, it means that it's a vector that has a start at the origin, but it's going to end somewhere. Sense. So that's what that 1, 0 and that 0, 1 for the I and J is you're saying I'm gonna start at the origin, but I'm gonna end at whatever the numbers give you and represent. So that's the standard or the standard basis vector, as they call it. And a unit, it's essentially a unit vector. A unit vector is a length of magnitude of 1, by the way. So that's why in the thing it said 1 and 0. So I probably should have, well, even if I already wrote unit vector on the article, but either way, those I and J's are unit vectors, which means that the length of that vector is exactly 1 unit depending on where you are. If you're on the x-axis, it's 1 unit to the right or to the left, depending on if it has a negative sign or not. And then for the J, which is the Y, you're just moving 1 unit up or down depending on what that is. But however you start at the origin, either way, it doesn't matter. So that's what they really are. I probably should have said that. All right. Moving on. All parallel vectors have the same unit vector. That'll take too much. Could eventually do unit vectors with cosine and sine, which is totally doable. It's actually not too hard. What you would do is essentially draw a right triangle that has a start at the origin. Actually, hopefully the camera can catch. Yeah, you eventually start a triangle that starts at the origin, kick it up a notch, and then this right here, if you can see, it's your cosine, that's your sine, and there's your hypotenuse. By the way, that's not tangent. That's not tangent. At the hypotenuse, we're not even considering that. But what we want to look at is the hypotenuse. Yeah, the hypotenuse is not tangent. The hypotenuse is our unit vector. The unit vector that has exactly a length of 1. Because I don't know if you remember, but cosine squared theta plus sine squared theta is 1. In a sense, you could do that here. So, but that's a different theorem in its own. But for a unit vector with for a unit vector that has cosine and sine, specifically for vectors, the cosine squared theta sine squared theta equals 1, that does not work. It does not necessarily apply here. But for that unit vector, you can do is cosine theta times the unit vector if you were going to move on the x-axis, which was the 1 and 0. That's what the I is. And then for the sine theta, that would be for your unit vector that goes up on the y-axis, if we were to draw that triangle up, essentially. So that's the twist in unit vectors for cosine and sine. It's just like if you were doing the regular, and by the regular I mean the regular is 1 and 0, 0, 1 for the standard basis vectors, except now all you would do is, instead of replacing it with the vector 1, vector 2, which we gave as the original 2 vectors that we used to have that end up looking like this. Now you're just saying, all right, this is cosine, this is sine. And that would be how you do it for trigonometry in a sense. But that's essentially the theorem in its essence. These are all just, these are just stuff. Yeah, this is these are practice problems, which, okay, so, I could tell this is it's not the best, but I have to proceed on. Done is better than perfect for now. But done doesn't also mean correct either. So, okay, chapter 11.2, vectors in 3D. So I already said this at the beginning, but you can do vectors in 3D, but now you got x, y, z axis. So that means your vectors, if they have those types of brackets, you're still saying that it starts at the origin, but now you have 3 points to consider. Where is it on the x-axis, where's it on the y-axis, and where's it on the z-axis? In 2D, you have 4 quadrants. In here, in 3 dimensions, you have 8, or like 8. You wouldn't call it quadrants, but octants, you know, say, where you could have a negative x value, but you're positive y and positive z, or you could have all three are positive, all three are negative, and then different combinations of it. Essentially, it's many combinations of the x and y values. Graphing it out, graphing in 3D might look a little bit funky, but for some people, depending on what you call your x or z axis, you could picture as the y. At least for me, I picture the y you picture the y axis as the regular one in 2D that goes up and down. Your x axis is the one that goes right and left. Your z axis would be like this, the one that if I were to draw the z axis, I would penetrate my screen. It would penetrate me too, and it would come out that way. So that's what the z axis is in a sense. So picture up, down, left, right, through and out. So that's how you would draw in 3D. But yeah, graphing out is a little bit funky on itself. There is and I have the proof up here that how one should graph, but I'm not gonna do that one right here because that's not necessarily useful. Because I'm not teaching. I'm just trying to explain as many theorems as I can. The distance formula, I don't know if you guys remember that distance formula, but essentially when you're trying to find distance is just basically like your length and magnitude in a sense for here, but sort of, not really. But when you try and find the length or distance of, let's say, x from the first point to the end point, you subtract your x values, square that, then your y and your z. But to do that, and as I mentioned, if you don't do that, you're just getting essentially half. So keep going. I mean, these are just examples proving that you can make isosceles triangles, but yeah, your midpoint is just like if you were doing it in 2 dimensions, where x1 plus x2 divided by 2 and y1 plus y2 squared. Circles and spheres, okay, it's essentially what we used to do with regular circles, which x minus h squared plus y minus k squared, where essentially you want to find where your center points, and then what is your radius there, in a sense, to find exactly what it is that one is looking for. Although it would be nice, actually, I would probably do the theorem for 2D. Actually, I'm going to remind myself. Theorem for 2D, and then a distance formula theorem. That'd actually be very good too. Actually, you know what? I might do that for the next video. No calc 3, it's just regular theorems, because I don't know, I like them because they prove things that are actually good formulas. Theorem, like why does it work? I like the why does it work, because if it works, then it's like cool. Then what else? All right, then complete the square. Yeah, okay. Find the equation of a sphere or at the opposite ends of a sphere where A, B are at the opposite ends of diameters, the center at the midpoint AB. Okay, so they just want the radius diameter of what A and B was. So it's essentially just applying the equations that I already mentioned. And then, vectors in 3D. So dumb. All right. Okay, so vectors in 3D. To find the length or the magnitude of anything of 3D it's kind of the thing where v1 squared plus v2 squared plus v3 squared and then square root that. So so nothing. There are these things where you're going to find that some vectors are scalar, like scalar multiples in a sense. All that means is that, let's say, I wish I had I'm looking for it, hold up. Okay, I can't actually find a pencil that's actually small. So, but scalar multiple vectors, all they mean is this. Let's say this was vector A and this was vector B. Let's say that this vector was 1.5 times bigger than this. All it means is that these two vectors, because remember, a vector is just a line in space that has a specific length and a specific direction. Anything that is a scalar multiple vector, it means that it will never touch each other. They can never touch each other. They will never do that. Because if they were, let me finish what I was about to say first, though. The scalar multiples just mean that this vector is the same one, they're just longer or shorter. That's all it is. That's what I mean by a constant times the scalar multiple. So I could say that if this is vector A, then this vector B, and I say 1.5 times longer, I could say 1.5 times vector A would give you the same as this. And if we just multiply this by 1.5, we get this guy. But that's essentially what it is. Because if they're that, then that means never cross. Okay, since I know I'm running out of time, so what I am going to do for part 2 is explain why parallel vectors never intersect. Okay, parallel vectors never intersect. Why? So that would probably actually be a lot more useful than all this shit that I'm saying. Parallel never intersect. Why? Okay. Hopefully I have enough time for examples. So fuck. These are parallel. Okay, this is a bunch of example. Oh, okay. Then the dot product, which whoever's took linear algebra, good for you. Yeah, if you want to do, you can multiply vectors. That's essentially what a dot product is. You can add the specific values of these vectors, but first you multiply the vectors and then you add all them up. So let's say if you had a vector of 1, 2, and 3, and 3, 4, 5, the value on the far end of the left is your x values, the ones in the middle are your y values, and then the ones on the far right are your z values. You multiply those numbers together, so x and x, y and y, z and z, and then once you get that, you add those 3 numbers together, and that's what you find as if you were multiplying 2 vectors in a sense. Because picture of it like this: if I want to multiply these 2 vectors, it's like saying smush together sense. And if you wanted to, yeah, because adding is essentially this: adding, subtract, multiply, boom. So then when you multiply these 2 lines, you're definitely gonna get a large y. But let's say if they have negative values, as if they shrink or something like that, then cool, that also may shrink. That either may shrink your vector, or that just changes the direction of the vector. Okay, so that's what essentially the basics of the dot product, and these are all examples. Properties of vectors. So I mean, you could just do this. Vector A times vector B is the same as vector B times vector A. Commutative stuff. Sometimes you have a vector of 0 which exists, which means it doesn't go anywhere. So it's like saying 0 times 5 in a sense. So the same thing with the vectors is you have a vector that goes nowhere and you multiply it by a vector that goes somewhere. Well, yeah, it's going nowhere in a sense. It's like going this times that. Well, now you got nothing. So it's literally multiplication, but with lines in a sense. So that's the one I would explain. And let's say you had two vectors that were exactly equal to each other, or two vectors that were the exact same, and you had to multiply them together. You're basically getting the length of those vectors squared in a sense. So it's like x times x squared. But instead of here, you're not getting those two specific vectors. You're getting the length of those two squares. That's literally what it is. Is you're multiplying to get a specific length, not a vector, specific length too as well. So that's how I would put it. And yeah, those are just properties. I mean, there's this thing of the law of cosines, which I'm also going to explain in a second video because I know I'm about to run out of time anyway. So with this law of cosines, essentially, you would draw your triangle. I mean, you could do the formula that goes with it, but even I'm not convinced. I don't like writing out formulas just for the sake of it. I want to understand where it comes from. But essentially, with the law of cosines, is when you draw out the triangle, when you draw the triangle to draw the cosine and sine and apply it to vectors, in a sense, the reason why the law of cosines helps well with it is when you start at the origin and you move around up here, it's most preferable to use the cosine rather than the sine, because you can always do that. And the reason why the law of signs doesn't work is what sign of zero? Well, that's zero. So in a sense, you're not able to really get the full beauty of being able to multiply the vector. So imagine if you always had to multiply at the start with just a vector of zero. Yeah, you're going nowhere. The cosine of zero is one, so that gets you somewhere at least. But yeah, when you go up to, let's say, cosine pi halves, then yes, that's zero. I know that's not the best explanation. I just need more time for this one, but that's how I would explain it. But just in this short time, so let's see. Parallel, V, the okay, these are okay. Okay, yeah, I'm going to need the I'm going to stop the recording and then I'm going to the notes that I have. Make another recording part 2 and then we'll do that. Okay. All right.